Hi everybody. In this video, this is the last lecture video from chapter 15. And we're going to talk about damped oscillations and resonance, which are in the last couple sections of the chapter in the textbook in chapter 15. So first of all, let's talk about damped oscillations. And what I mean by that is that there's some kind of friction or resistance resistive force to the oscillations. Now, the way this could come about is that you could have your spring and it's in a fluid. It could be the air, or you could actually have it in a vat of fluid or something, but there's some resistance to that oscillation. For a fluid, it turns out the resistance force, or the damping force, is proportional to the velocity if you're not going too fast. At higher speeds, for example, if you're talking about air resistance of a jet or an airplane, it might be proportional to the speed squared. But damping is kind of like friction. We don't have a good theory or theoretical calculation of it. We got to use a formula that's derived from experiment or empirically. So we're going to consider our force that's damping, but first of all, we remember that for a free oscillation, we found that we had simple harmonic motion. And Newton's second law tells us, right, the sum of the forces, the only force is Hooke's law, negative kx. That's equal to mass times acceleration. And that was where we found our x of t equals a, an amplitude, times cosine omega t plus 5. Right, and omega is the angular frequency, natural frequency that the spring would oscillate at. So now we're going to put in or add to our Hooke's law force our damping force, which is proportional to the velocity. And we're going to write it as negative b times v. V is a damping constant that would depend on the fluid or what is actually causing the damping force. Again, v is the first derivative, dx dt. So plugging this into Newton's second law, we add our damping force to our Hooke's law force and set those equal to mass times acceleration. Just rearranging a little bit, bringing everything over, we get this differential equation for x again as a function of time. So to solve this, I'm not going to go ahead and go through the differential equations. If you take a differential equations class, you might study things like this in more detail. But just physically, you can assume, right, that there's going to be some oscillation involved, especially if the damping constant v is small enough. There's going to be some oscillations, but those oscillations are going to die out. And by that, I mean the amplitude is going to die. So you might guess, okay, well, there's an exponential decay of the amplitude times a cosine. And this is the actual form of a solution. It turns out there can be other solutions to this differential equation. But this is the physical one that makes sense. You've got an amplitude that decays away exponentially as a function of time, depends on your b and your mass. You've got a cosine and oscillation. Well, it might make sense that your frequency changes a little bit, right? It might actually lower as you have more damping. And in fact, if you just plug this equation in, you can actually show, similar to what we did for the free oscillation, that your new angular frequency is square root of k over m minus b squared over 4m squared. Right, if b is 0, it just gives your square root of k over m, just our original free angular frequency for that free oscillation. So as we see, the amplitude depends on time. It decays exponentially. And I think there's a homework problem where you can use this equation to figure out what is the amplitude at any time. And again, you know, as the b constant is bigger, you'll get a faster decay. If the mass is bigger, you'll get a slower decay. That makes sense, right? It takes more time to slow those oscillations down. We could also calculate the energy as a function of time. Just plug it into our 1/2 kx squared, and you get this expression. Again, there's an exponential decay of the time, or decay with time, of the energy from its maximum starting value. Okay, so those are our damped oscillations. Now we can consider another situation. What if you have a forced oscillation? What I mean by that is that I have a mass in a spring, but I'm going to push it. So one kind of example of this sort of thing is, let's say you have a support you've got the spring hanging from, but the support can actually be moved up and down. Now, as you do that, what physically can happen here? Well, it's going to depend a little bit on how fast the damping occurs or the forces occur, but we have a frequency of the pushing or the forces that's going to be applied. So we're going to assume, just for a particular case, that our pushing force has its amplitude F0, and it's got a frequency omega p, right, an angular frequency. If we had no damping, so we're going to take away the damping for now, we've got our Hooke's law force plus our pushing force, or force oscillation. Those are our two forces. Newton's second law says add those, set them equal to mass times acceleration. Now here's another approximation that we can get a solution for. I'm going to assume that the solution ends up being the same frequency as the push. Now, you can have different kinds of motion, but this is one particular solution. Turns out you'll always get this particular behavior that we're going to see. So what I would do is I would assume this solution, plug it into Newton's second law, and I get this, right? Taking two derivatives, I pull out a negative m omega p squared. You find all the cosines cancel, and I get an equation like this that I can solve for my amplitude. So dividing by m, doing a little bit of algebra, and using that omega squared, my natural frequency is k over m, I end up eventually getting an equation for the amplitude that looks like this. Now this is physically what I wanted to show here. The amplitude has a value, but it's got in the denominator a thing that can actually go to 0, right? If my natural frequency is equal to the pushing frequency, the amplitude actually becomes infinite. So when omega p equals omega, right, when my pushing frequency equals the natural frequency of the spring, I get an infinite amplitude, a huge amplitude. And this phenomenon is called resonance. It happens for anything that oscillates. If you have anything that oscillates, it's got a natural frequency. If you push it with a pushing frequency that's equal to that natural frequency, you will get a large amplitude. A couple of examples, one that you're probably familiar with, let's say you have a child on a swing at the playground, right? If they just swing back and forth, they've got a natural frequency, like a pendulum. How do you get their amplitude really big very easily? Well, one way, right, you push them really hard one time. Well, that might get them high or a pretty large amplitude, but there's a better way. What you can do is push them a little bit, wait until they go out and come all the way back. They've gone through one cycle, push them again just as they're starting the next cycle, right? And keep that up. You are applying a force that's equal to the natural frequency, and you get a large amplitude. The child gets really high. You transfer energy very efficiently by pushing at the natural frequency of the child on the swing. Again, this can happen in any oscillating situation. For example, in the old days before soldiers used vehicles, they marched, and they would be taught as they march across a wooden bridge to get out of step with one another. Because if their marching frequency of their footsteps happened to equal the natural frequency of the bridge could actually start swaying and collapse. So there are a number of situations like that. Even electrical circuits that oscillate have a natural frequency, and you can get resonance occurring there. So resonance is a pretty common phenomenon. Even in medical imaging, magnetic resonance imaging, MRI, the resonance refers to a situation where you're matching a pushing frequency to a natural frequency. Now, I should mention that if you did have damping, the amplitude does not become infinite, right? Let's take the ratio of my pushing frequency to my natural frequency. When it equals 1, they're equal. With damping, you'll get a large frequency, but it will not become infinite. And the more damping you get, the lower the frequency. But again, resonance means pushing frequency equals natural frequency, you get a large amplitude.